I wondered if anybody was on. My name is Robert Stevens. I'm your moderator this morning. We have several distinguished panels guests this morning to speak to us. We have Mr. Ron Hager, who's a project manager with Burns and McDonnell. A little fun fact about Mr. Hager was that prior to this conference, during COVID, he had grown a Viking beard and he trimmed it for us. Next is Ms. Rachel Klinger, PE, BCEE. I feel like Vanna White. I want to buy another vowel or something about that. But anyway, she is a proud parent, and had 5 minutes of that experience has been fun. We also have Mr. Michael Gefell. He is a PG, C.P.G of Anchor QEA LLC. Wow. Mr. Gefell is going to Siesta Key after this, not to go see the mouse. So we wish him luck on the beach. If you would hold your questions to the end of the presentation, there'll be time for questions. We appreciate your attendance this morning. And Mr. Hager is going to start us off. Thank you.
Good morning, everybody. Normally I talk without a microphone because I'm pretty loud, so I don't normally need a microphone, but we'll go ahead on anyways. As a fine gentleman said, my name is Ron Hager, Senior Project Manager with Burns and McDonnell. I wanted to start off and thank my co-authors, Ben Clement and Scott Myers, who were both very instrumental in the success of our project, but had nothing to do with this presentation. Thank you. I'll go ahead and introduce the site. As you can see, this presentation is about a large scale in situ solidification stabilization project that we performed during COVID and some of the challenges that we faced as we moved through that project. The client was Ameren. The site location was in Macomb, Illinois, so it was a former MGP site. The contractor was North Star. The chosen remediation method for this site happened to be ISS, and we did ISS to approximately the maximum depth was about 68 feet. So we ended up doing a combination of bucket mixing and auger mixing to achieve our remediation goals. We started off, and let's try the clicker here. There we go. 1.2 acres was the size of the site. We had about 15 or 20 workers on site every day on average. It would increase or decrease depending on what we were doing. As you can imagine, there's a lot of things going on during an ISS project. You've got the batch plants, you've got on-site water treatment and dewatering. We had the two different operations going on at the same time, bucket mixing and the ISS auger mixing. So there was a lot of people on site. We started, so we finished up our site investigation around June of 2019. At that point, we went into the design phase and the bidding phase. We mobilized to the site in January of 2020, ready to go with our remediation activities. And we actually started at the very beginning of March. We broke ground and started performing our ISS. And then on March 11th, lo and behold, the CDC, or the World Health Organization, declares that COVID is a pandemic and everything comes to a screeching halt. Luckily for us, Ameren was deemed essential. And so we were able to get authorization to continue working because Ameren was essential. So we decided that we were going to go ahead and push on. And then remediation was completed in October. So as you can see, we worked from March until October. So, approximately 7 months that we performed the remediation during COVID. So when the declaration came down that it was going to be a pandemic, we got all the parties together. Ameren and North Star and Burns McDonnell got together and had a big meeting, and we had to make a decision whether to mothball the project or whether to continue on. All parties agreed that we could sit down and come up with a good set of guidelines and protocols in order to complete the project and still maintain, safety of the workers and everybody involved. So we sat down, and between March 11th, when it was declared a pandemic, and April 10th, we utilized the CDC guidelines as our standard protocols for the site until we developed our own. So we sat down. Ameren came to the table with their set of guidelines they wanted to see implemented. Burns, McDonnell, and North Star brought theirs as well. So we sat down and we kind of came up with a compiled list of everything that we wanted to implement at the site to make sure that everybody was working safely. A couple of the things that we came up with that were very important to us was to make sure that everybody communicated if they felt that there was something going on that wasn't going to be safe, or that they were going to have an unnecessary exposure. Some people believed in COVID, some people didn't believe in COVID. So we made sure that everyone respected everybody's opinion and to work together and to address any potential concerns that people had. And if we weren't able to resolve the concerns or issues at the site, then we would escalate it up to upper management, and it would be taken care of offsite. So one of the first things we did is we basically closed off the site to anybody that wasn't actually part of the project. So anyone that was not deemed to be essential, visitors, things of that nature. We had people from the city that wanted to come out. We had people from the IEPA that wanted to come out. We shut the gates and kept the gates closed, even during working hours. We had an office building, and everybody that came to the site had to go through the office building in order to gain access to the site. Lucky for us, we didn't have to use trailers as our field offices. There was an existing building on site, and it was a very large building, former mortuary building, I think, and it was 3 stories and had 20 plus rooms in it. So we were able to have everybody that was in the office had their own space, and so they maintained the 6-foot distance. But everybody was kind of corralled and had to funnel through the office building before they were allowed on site. And so when they came in the morning, all the workers had to come in. We had thermometers there, the no-touch thermometers. They had to take their own temperature. They had to record their temperature every morning. And then there was a questionnaire that they had to fill out. And I've got a copy of that questionnaire I'll bring up here in a second. And they had to fill out a questionnaire, and it had questions like, have you traveled recently? Did you take public transportation? Have you been in contact with anybody? Have you had a COVID test recently? Has anybody that you've come in contact with had COVID or had a COVID test? Things of that nature. So every employee that came on site, regardless of what company they were from, had to fill this out and had to have their temperature taken. It was all recorded, and it was kept for obvious reasons. So another thing that we had issues with is that, as you can imagine, working on this site, we needed a lot of Portland cement deliveries for our batch plants. So we had to schedule the deliveries in advance. That way we could know when they were coming on site, open up the gates, allow that person to come in. They weren't allowed to get out of their truck. So we'd had to divert extra people over there to help with the emptying of the trucks. And anytime we got deliveries, those people had to go over there and make sure they could unload and accept the deliveries without getting within 6 feet of each other, and it all had to be coordinated. So that was something that was kind of a little different than the normal procedures that we would use on a site. One thing that was actually kind of very helpful on this is we didn't have any supply chain issues as far as any of the materials that we needed, any of the equipment we needed. We didn't have any slowdowns, delays, or anything related to COVID, which I know a lot of businesses experienced that during COVID, was, delays in the supply chain. We didn't have any of those, and that had no impact on our schedule. So that was one thing that was very beneficial to us. Here you can see the questionnaire. Hopefully it's not too small for you to read, but like I said, there's several questions. They had to answer no to every question. If they answered yes to every question, then or to any of the questions, then we had to do further investigation, and they may have been asked to leave. We had a mandatory 10 working day quarantine for anybody that had an elevated temperature. They'd have to go get a COVID test, and then they'd have to sit out until they got the results of the COVID test. If it came back positive, it was a minimum of 10 days quarantine before they were allowed back to the site. Other challenges we had is that, as you can imagine, this is a specialized construction project for remediation. And so you've got people that know how to run the augers. We have people that know how to do the bucket mixing, and that's kind of specialized operators that you use for that. And if you were to have a few of those operators that came down with COVID and had to be quarantined for 10 days, you certainly have a labor shortage there, and it kind of brings the project to a screeching halt. So we had to make sure that one of the things we did was to train multiple people to run each position. So we had to have people that knew how to run the batch plants, multiple people that knew how to run each piece of equipment. So that way, if we lost any of those people to COVID, we'd have people that would be able to step into their place without creating a schedule delay for us. On-site directives were that the workers were required to maintain a 6-foot separation distance at all times. As you can imagine, on a construction site, that's not very typical. Again, we didn't have to use trailers for our office space, so that made it much easier to keep a 6-foot separation for everybody. People didn't have to come into close contact. We took any of our meetings that we had, and we tried to make as many of those meetings virtual as possible. We eliminated as many of the meetings that were on site and together as possible. So you literally had people sitting in other rooms doing Zoom meetings with each other, as opposed to getting together and meeting. The typical tailgate meetings that we would have in the morning, the contractor would, once we were outside, you didn't have to wear masks, but we tried to keep everybody 6 feet away during the tailgate meetings. And that proved to be somewhat of a challenge because, as you can imagine, it takes a lot of coordination to manage a large scale operation on a 1.2 acre footprint. So it was important that everybody knew what they were doing that day, what their responsibilities were. And so you had to try and communicate that while keeping everybody at a 6-foot distance. So you had to make sure that the communication was very clear. Hand wash stations, that was another thing that we did. We put in hand wash stations in several locations. As you guys can probably guess, we had hand sanitizer bottles literally everywhere. We had bottles of wipes everywhere. Inside the office building, we got rid of the common coffee makers and things of that nature where people would tend to gather together. We had to eliminate all of that. We had to use bottles of water as opposed to having a water system there for people to drink water from. Anything that would draw people together or where people were sharing things, we had to eliminate all that. So that was another challenge. Lunches, things like that, everybody had to sit apart from each other. So and everybody was fairly did fairly well with that. There was a few people that were actual North Star employees that came in and they had to travel in. I think the majority of them were from Florida. The rest of the people that we had on site were out of the local union halls. So at least they weren't having to travel. When we had holidays and weekends, they were just going home. Anybody that traveled, we had to do had to get passing COVID tests before they were allowed back on site. And anytime that you were inside the field office, they requested that you had a mask on. Another thing we had to do is we had to have shutdown procedures in case we had an outbreak of COVID on the site. So we came up with a list of things that we would do if we had an outbreak. Lucky for us, we didn't have an outbreak of COVID during this project, so we never had to institute these procedures. But we had to work quickly to stabilize the project, make sure that there weren't going to be any safety concerns. We had to de-energize everything. We'd have to shut down the equipment, get the equipment that couldn't be left on site safely would have to be removed. So North Star would demobilize that equipment. We had to leave people on site to get that demobilized. And of course, we'd maintain regular communication. And then once we were past the point where we had that outbreak and everyone was back safe and healthy again, then we would all meet back at site and remobilize and start the project over again. Another thing is we had to get the local union to agree to all our protocols. So that was one of the things that was a little challenging, was to sit down with the labor union and make sure that they were okay and felt like their workers were being protected. So in conclusion, all the site personnel were monitored on a daily basis. Everything was documented. We kept everything, all the records. Project team was prepared to respond to any COVID-related incidents. Like I said, there was a 10-day minimum quarantine for anybody that came down with COVID or had any COVID symptoms. We did testing every single day with thermometers. If you left the site, you came back to the site, you had to use the thermometer to make sure that your temperature was still down. We were prepared to make staff adjustments, replace any of the important workers and operators that we had that were doing specialized work. We had to have backups for them, which we did. Our project was very, very successful. All the protocols and guidelines that we put in place were successful, and we were able to complete the 7-month project without having any COVID-related delays, lost work days due to COVID. And it was due to the diligence and awareness of the entire project team, North Star, the contractor, Ameren, the client, and Burns McDonnell, the engineering consultant. Everybody worked together, and we had a very successful project. And not only was it COVID safe, but it was also a very successful project. So that's all I have to say about that.
Good morning. Thank you. I'm glad you're all here today. For those of you that aren't, I'm sure you had a great time last night. I'll try to keep this interactive. I want to start with kind of giving some background on mass flux. I always appreciate some just quick technical reminders before we jump into case studies. So that's how my presentation is going to evolve. Before we start, though, I want to acknowledge a couple of the contributors to this project. Jeff Foster is with the city of Jacksonville. Jeff, wave your hand, say hello. Bill Pence, he's with Baker Hostetler. He's an environmental attorney that supported this project. Dr. Mike Annable with the University of Florida, and a couple other of my colleagues at Geosyntec, with a specific note to Ashley Ramsey, who led the field efforts at the site. So quick overview of mass flux, real quick. So, mass flux refers to a contaminant mass that goes over a surface area over a given period of time. It's influenced a lot by the groundwater flow gradient and velocity, and how much dissolved contaminants are in place over time. So most decisions, when you think about a remedy to clean up a contaminated site, involve what contaminants are there, what are the potential receptors to those contaminants, and what are ultimately the cleanup objectives that we need to establish to either decrease the risk to the receptors with the contaminants in mind. So understanding mass flux is really important to this concept. And as you can see here, and this is a figure from the ITRC document, contaminant mass flux changes throughout the course of the plume, and it's heavily influenced by your conductivity. So assuming you have the same concentration across various lithologies, you're going to have higher mass flux and higher permeability zones. It's also going to be significantly impacted by soil absorption coefficients and the organic content in the soil. And then, of course, the microbial community that's degrading contaminants in place. So how can this help us? Just the understanding of mass flux and how we're achieving our goals. How can we use it? So first we use it to evaluate risks and the potential for exposure at receptors. And we use it to assess plume stability and M&A. But it can also really aid in the selection of appropriate remedial goals and objectives to address the risk. So remedial goals can be developed to address a source until mass flux is removed at the point of a receptor. And Chad Northington, if you were able to catch his presentation yesterday on PFAS and the plume stop, gave a really good example of how understanding that mass flux helps design a barrier wall to mitigate that plume migration. When we think about this, you think about, selecting the right tools. And I often think about them as like selecting the right hammer. And we've seen a lot of really heavy hammers like ISS and large scale excavations. But it's also important to note that you don't always need a heavy hammer. And it's important to understand what that contaminant mass flux is at the receptor and what your cleanup objectives are. Because in some cases, a smaller hammer could be sufficient as well and adequately addressing your remedial goal. So again, just continuing on with a high level overview, what methods are available. So these are 3 methods that ITRC presents. The 2 common ones are using of transects, where you have discrete contaminant data points and groundwater characteristic at each, and you're evaluating mass flux across a plume from data collected in permanent wells or piezometers. And the next most common one is by deployment of passive meters. And those are devices that you put in wells or in a borehole that will absorb contaminant mass as it travels across the meter. And as water passes through it, traces are released. And by evaluating the contaminant mass on the meter and the tracers removed, you can calculate mass flux. So there are several meters that are available. These first 2 are focused on mass flux. We use the ones developed by UF, but there are other companies that also develop these types of meters. So the first one, just going into a little bit more detail, the passive flux meter, that's really measuring that horizontal mass flux across the meter. So again, it's got absorbent media inside that retains the contaminant mass as it travels across. And as water is bypassing that meter, the tracers are leaving, and the combination of those 2 things allows you to calculate your mass flux. Sediment bed passive flux meter. So in some cases, you have contaminated groundwater that could be upwelling or discharging into a surface water meter. So assessing the vertical mass flux into a receiver is also really important. So these are similar to the PFMs, but instead of measuring a horizontal flow across the meter, it has 2 screened intervals, and it allows a vertical passage of groundwater across the meter. And then these next couple aren't flux meters. These are devices that are deployed over a period of time to assess and quantify the concentration of contaminants in place. And serums SP3s pick up a lot of PAHs, OCPs, dioxins. Serums peepers can do inorganic compounds like metals, nitrates, phosphorus, etc. But those are deployed in situ in devices left over a period of time to evaluate what concentration of COCs are present in either pore water or surface water, and they can also be deployed in groundwater. So there's a lot more than just these 4, but I wanted to focus on the first 3 because those were the ones that we use and I'll present on during our case study. So Main Street MGP. So in the late 1800s, an MGP operated and served the Jacksonville community. And like all MGPs, it left a legacy that keeps us all busy and attending conferences through the years. But over the last several decades, century, a lot has changed at this site. So most notably is the channelization of Hogan's Creek. So you can see it meander down gradient of the former gas holder. And today that gas holder is kind of up gradient of the Napple area that is shown in blue, but you can see that Hogan's Creek has now been channelized. And the important thing to note is that the channelization and where those two surface water features that are there today overlap with Napple impacts in place. So Napple and other visual impacts from former MGP operations are in place. They're predominantly observed between 15 and 35 feet below land surface, and they're within and below the peat layer. And that peat layer is really a relic of the old creek bed associated with Hogan's Creek. And that's where largely a lot of the discharges from the former MGP were discharged. Over the last 100 years, the groundwater impacts consisting of both PAHs and BTECs have stabilized. However, there's still concerns, or there were concerns, that the presence of Napple and the highly impacted groundwater concentrations were discharging and impacting the two surface water receptors due to that a strong upward gradient at the site. So as part of our pre-design planning, we anticipated the need for source removal of mobile Napple impacts. And it was contemplated that would be done using multi-phase extraction. And we also, as part of the planning, needed to understand what that mass flux was into the surface water body, so we can also design for that elimination, the mitigation of that mass into those features. So we developed several work plans. We developed an MPE work plan to do pilot testing, pre-design, and then we also did the mass flux work plan that I'll talk about later. We implemented the mass flux work plan first for a very good reason. We didn't want to install MPE wells across the peat layer into the source before we deployed meters to establish what the equilibrium was before we sort of penetrated into the Napple at the site. So the mass flux work was done first. Okay, so our objective was really to quantify where is the highest mass flux coming into the creek so we can design to that. So our study involved evaluating the base type at the site, which included also an evaluation of sediment thickness and temperature gradients between surface water and pore waters. And we aimed really to collect data to help us identify those highest mass flux areas. We installed nested piezometers to confirm lithology, confirm where Napple was present, organic content of the peat layer, and to help deploy the PFMs in the piezometers as well as part of the study. As a team, we also thought, because it is not always easy, we've heard a lot about, expect the unexpected and obstructions underground, and that is certainly the case in old creek beds and rivers. So one of the things we thought of in advance was, well, let's test out the deployment. Can we actually get these meters in the ground? How deep can we get them? And do we need to redesign some of them based on what we're seeing? So during our pilot deployment, we deployed serums SP3s, and those were deployed in groundwater, pore water, and surface water. And that was to evaluate the PAHs in those medias. And then we deployed UF's PFMs in the groundwater and the SB PFMs in the sediment to evaluate pore water. And those were really to evaluate the BTECs mass flux. We also did some biotrap analysis towards the end to evaluate degradation capacity of the microbial community and degrading naphthalene and benzene. So we did a lot of work, and this is where Ashley gets a lot of kudos. So during site reconnaissance, she collected data at 225 locations and 148 through that pond. And she looked for base types, sediment thickness, and temperature gradients. The base type was to evaluate if there were areas that were more or less pervious. So there was past data indicating that there were various types: concrete, cedar plank. In some cases, there was nothing. For the temperature gradient study, we did two things. We looked at a survey with, traditional RGB and IR to see where upwelling was occurring. And then we also did in situ measurements where we deployed a YSI temperature probe right at the sediment interface and collected a measurement there. And then also advanced it about 6 inches to a foot below the sediment to evaluate what was, groundwater upwelling, and then looked at those differences to see if that could help paint the picture of where mass flux and preferential places for discharge were occurring. So here are some of the results. So starting with the graphic on the right, the pond is that really colorful one that meanders a bit. The red is the concrete. The purple is the cedar plank, and that was part of the channelization of Hogan's Creek in that construction. The areas in green where we didn't observe anything several feet down. And then we overlap that with the Napples. The idea was, if there was upwelling, where would it preferentially flow? And that would be in places where there is an impervious surface. And then the areas in the black are where we noticed a change in that temperature gradient that would be more indicative of an upwelling of groundwater into the surface water body. So we use that data to deploy our locations, our samplers in locations that were very conservative. So we deployed in areas where there was no base type present, so nothing to restrict upwards migration, preferential flow. Within Napple extents, we confirmed that with the installation of piezometers. And we also wanted to look at mass flux above and below the peat, because we knew the peat was serving as an area to hold a lot of the PAH and benzene mass. So here's a cross section to just better visualize where we deployed what meters. So all right, wrong button. All right, so like I mentioned earlier, we have meters in the groundwater, we have meters in the pore water, and then we also deployed surface water samplers. We have the PFMs and the SBPFMs, those are UF, and those were primarily focusing on the benzene in both the groundwater and in the pore water areas. And then we use the SP3s, also deployed them inside the well, but also in situ next to the SP3s and also in the surface water. So here's what we found. I'll start with BTEX and I'll walk through this figure because there's a lot to show. The plus signs, those are groundwater samples that we collected. The triangles are where we deployed PFM samples. And what we were finding is that below the peat, where there was Napple, there was of course high groundwater concentrations. But as you moved within the peat, we still had at least in one transect Napple that was present in groundwater that exceeded. But moving forward above the peat, we started seeing groundwater concentrations less than the cleanup target level, as well as the surface water cleanup target level. So we were kind of building the case that, yeah, there's Napple present, but as you progress vertically upwards, as mass flux is, discharging into surface water, there isn't a risk to that receptor. So BTEX, no longer a risk. And so next we looked at the PAHs. And similar to BTEX, clearly we were finding concentrations below the peat and within the peat. And even above the peat, as we were progressing to the surface water body, we were still seeing detections. So we had meters that were deployed about 4 feet below. We ended up seeing a significant reduction in the groundwater concentrations in those. So we ended up going back and deploying another one at a foot to just try to get a better look at how that changes as it's discharging. And we went from exceeding from about 5 PAHs to just 1 in that 1 foot sample. And then we confirmed that it was no longer an issue when we deployed the meters in the surface water body. Okay, I skipped ahead here. So with that said, all of this data was clearly telling me I wasn't going to design a really cool MPE system anymore. But it was showing that it wasn't necessary, which was really good for Jeff. Our new CSM really boiled down to, although NAPL is contributing to high groundwater concentrations, exceeding groundwater concentrations, based on the data from our study, it didn't ultimately result in any mass flux and no material discharge into the surface water body. And that presence of that peat layer that I mentioned earlier enhanced that absorption capacity. And the documented microbial population also served to support natural ongoing attenuation of those impacts in a vertical upward direction. So the type of lithology and the absorption capacity for our COCs had a huge impact in really reducing ultimately that vertical mass flux that was previously thought to be occurring and requiring treatment. So we were able to conclude through this that those MGP impacts at the site don't pose a risk and are likely in the long term, unless there's changes to the base type of the creek in the future. So finally, I'll end with just a few lessons learned. The first one being there's significant remedial cost savings that can be achieved through enhancing your understanding of CSMs. We have heard so many presentations throughout the course of these two conferences where that proves true. But sometimes it's hard when there's a cost that comes along with additional data collection. But it more times than 10, or more times than I can count, always proves to be true. And in this case, we ended up working ourselves out of a cool design project, but it wasn't necessary to begin with. Also, engineering controls can be ineffective means. We all know that, we all use them, but sometimes when you're working with the agencies, you have to give them the data to demonstrate that they're effective and help them agree with the recommendation that you're providing them. I've alluded to the fact that these samplers, to deploy them, are super tricky. So plan for the unexpected. And if you are going to look at the study, those pilot tests are really helpful. Finally, the legacy sites have been around for a while, hundreds of years. And depending on the source area and site-specific conditions, this established equilibrium that happens over time can sometimes overweigh, especially in this case, an expensive source removal project. Thanks.
Well, that was a great introduction for my talk, because I'm also going to talk about mass flux. I'm Mike Gefell. I'm with Anchor QEA, and Rachel's talk was a perfect introduction for this. So I'm gonna speak specifically about mass flux assessment for remedial design in settings where sediments are contaminated. And at MGP sites, we can have dissolve phase issues, and we can also very commonly have NAPL present in sediments. So I'm going to talk about both phases. Before I go on, I'd like to acknowledge Kevin Russell, Deirdre Reidy, Billie-Jo Gauley, and Mike Rury, who helped prepare this presentation. So I'll introduce what we're trying to achieve with typical sediment remediation projects and how mass flux fits into that objective and that endeavor. And then I'm going to spend a fair amount of time talking specifically about dissolve phase mass flux and then NAPL phase mass flux, because both of them are essential to quantify for effective remedies. And the area of interest for this discussion is in the sediments right under a water body in close proximity to potential receptors. So there's little wiggle room. So accurately quantifying mass flux is essential for developing a reliable remedy. So usually at sediment sites where sediments are impacted above risk-based standards, and typically we're looking at ecological risk-based standards, but sometimes also human health risk-based standards. In those situations, what we want to achieve is a situation where the risk-based goals can be met, and where they're predicted to be met for a very long time. Typical design timeframes are 100 years or so. If we're in a situation where the risk-based goals are already met, then we don't need to quantify mass flux in detail. But if they are not met, then we need to implement a remedy, and we want to be able to design that remedy for long-term reliability. And mass flux is crucial for that, because that influences how much sorptive material we might need, for example, to be able to block the upward movement of either dissolve phase, mass flux, or else NAPL phase. So a little recap: mass flux in its basic form is concentration times flow rate. And we're talking about two fluid phases. There's the dissolve phase, and there's also the NAPL phase. So we need to quantify the mass flux of both of these. The dissolve phase is crucial. And with sediment remedies, what we're trying to accomplish is clean pore water in the top few inches of sediment. That's the bioactive zone, and the pore water is the bioavailable phase. But the NAPL mass flux is crucial also, because the dissolve phase typically is coming from dissolution of the NAPL phase. And so if the NAPL is moving upward over time, then at some point in the future, the dissolve phase concentrations could become a problem. So let's start with the dissolve phase. And the two fundamental components of mass flux are the seepage rate and the pore water concentrations. So let's look at both of those. Pore water seepage in sediment settings is a fascinating and complicated topic. Let's start by just looking at this diagram down here. We have a situation where we have sediment, we have overlying surface water. The surface water flow is going from left to right, and we have overall upward pore water discharge through the sediment. But because of the interaction of the pressures at the surface of the sediment along these ripples, we get these small zones where there's actually flow going from surface water into the sediment and then back out. And that's known as hypereic flow. We also get the opposite in some cases. You can have a site where you've got a large groundwater extraction system right along the shoreline where you've got net downward flow, but you also have these anomalous little cells where it looks like the flow is coming back out, but that's only because of hypereic flow effects. So we know that seepage is variable because of hypereic flow. We also know that it can be variable because of heterogeneities within the sediment. So we have to collect data in multiple locations to be able to characterize it across the area of interest. And when we select locations for sampling, we consider things like stratigraphy, geomorph, and areas where we know we have concentrations of concern. Seepage is also temporally variable. And in some settings, on flashy river systems, for example, it can be significantly temporally variable. There also are shorter term effects like tides and storms that come into play. The data set at the bottom is a 4-month period showing the vertical hydraulic gradient. And we can take hydraulic gradient data like these and multiply them by the vertical hydraulic conductivity to characterize seepage for long and continuous periods of time. This is just one example data set from a relatively flashy river. And what we see is that the hydraulic gradient can vary significantly. So what that means is that if you're using a seepage measurement method that gives you a snapshot measurement at one point in time, you should do that more than one time. You should do that a bunch of times to get an understanding on what the long-term average seepage rate is, because that's what you need for a long-term remedial design. Another alternative is just collect long data sets like this. And then you can take into account all of the variability, basically, and calculate a good long-term average. So to measure seepage, there are two fundamental methods, kind of like industry standards. And the first is to install piezometers, like I'm showing here on the right. We've got a couple of piezometers with short screens down in the upper portion of the sediment, and they stick up above the surface of the water. And so you can put transducers into those, get long-term data sets like I just showed, and then you can measure the vertical hydraulic conductivity between those screens, and then you get a long-term data set of seepage values. Another option is to use seepage meters. This is an electromagnetic seepage meter that we used at a site with the USGS and placed it right into the surface of the sediment. And the seepage meter measures the flow rate and direction over time. And then there are other methods that are also being developed, but are not yet in as common use as piezometers matched with permeability data plus seepage meters. Now, with each one of these measurement methods, I want to point out potential pitfalls. And seepage meters are great, but they're point measurements. And because of hyperetic flow effects, you can get anomalous measurements with seepage meters. And in some cases, they can actually be fouled. This little ghost shrimp produced anomalous data in a seepage meter, an electromagnetic seepage meter, basically by fouling the flow meter device. Also, ebullition gas that comes up into seepage meters can complicate use of the seepage data. And there can be complications with putting seepage meters in sediment that is very soft. It can be difficult to install them if the sediment surface is too hard. They have battery lives that typically are on the order of a few days. Piezometers are great, but if you have a flashy river system where you've got strong flow, or if you've got a navigable waterway where you've got vessels, or if you've got debris or ice flows moving through the water, they can get wiped out. But there are advantages in getting long-term data sets. So what we really need is a workaround for that. Another issue with the piezometer approach is to measure the vertical hydraulic conductivity between those screens. Standard methods would be to collect cores, cut them into about half-foot long sections, and send them to the laboratory for measurement of vertical hydraulic conductivity using an ASTM method. But if your screens are separated by 5 feet, that's a lot of samples to send to the lab. You have to cut them, you have to ship them, they have to put them into the measurement device, they have to measure them, and then you have to mathematically figure out what all of that means in terms of the bulk vertical hydraulic conductivity. So to get around some of these pitfalls, particularly piezometers getting wiped out and vertical hydraulic conductivity measurement complexities, there are some economical things we can do to get good data and to get around those problems. So the issue with the vertical gradient measurement devices getting wiped out, there's two solutions that have recently come about. Dr. Rosenberry, Dr. Donald Rosenberry at the USGS, developed what he calls vertical hydraulic gradient devices, or VHGs. So this is a single rod. It's got 2 screens that are hydraulically isolated. Each screen has a transducer in it. And basically you can just push it into the surface of the soft sediment and then record a data set for as long as the transducers can record data. Another alternative, if the sediment isn't soft enough to push in a VHG, so you have to drill, is you can put in a pair of piezometers and instrument them each with transducers and cut them off just above mud line, and then put on watertight caps. And you can still measure the vertical hydraulic gradient, but since they don't stick up very much, they're not anywhere near as prone to being impacted by whatever might be moving through the river system. And then for vertical permeability, the way that we advocate for measuring vertical hydraulic conductivity between the screens of piezometers is to get representative big long sediment cores, like 5-foot long cores, keep them vertical, put a perforated cap at the bottom with filter material, and just allow gravity to drain pore water slowly out of the core. And in a total volume of drainage on the order of maybe 20 milliliters to 200 milliliters, we can get very continuous, consistent flow rates that we can convert to vertical hydraulic conductivity for that whole length, that whole 5-foot length in one measurement. And we can do those in the field, and they're inexpensive. So it's helpful to get the big picture, try to avoid that superficial area where hyperaric flow is happening, and collect continuous long-term data. Well, what about pore water concentration? So we have to match the flow rate with concentrations. And in sediment settings, it's very common for concentrations to also be spatially variable. And so we know that we have to collect pore water concentrations. We know that we're interested in measuring them in the upper few inches of sediment, or if we know that dredging is going to happen to a particular depth because there's an obvious impacted zone that is going to come out, then we want to measure it at the proposed dredge cut. So we understand what the dissolved phase concentrations are right there. That will be the surface that it will be exposed in the future. And common measurement methods for pore water concentrations, you can collect the samples by pumping. You can use push point devices like these and pump samples out of them. You can use passive sampling methods like solid phase microextraction or SPME fibers or polyethylene samplers like the SP3. And those devices are also very useful, and you can measure concentrations down to very low levels. And you can estimate pore water concentrations by partitioning calculations with bulk sediment samples also. But there are potential pitfalls in attempting to measure concentrations in sediments. For example, with the partitioning method, we know that different types of carbon have different affinity for the parameters of interest, which is typically PAHs, PCBs, and the like. Also, it may be difficult to get sampling devices into the upper few inches of sediment. Also, if you are trying to do a pumping method, if you insert a push point into the upper few inches of sediment and you want to pump a sample out, you run a risk of pulling surface water right into the sample that you're collecting. And at MGP sites, there's a really, really big risk that NAPL is present in the sediment in the upper few inches or at whatever depth you need to collect your pore water samples at. And because NAPL is present, that creates a risk that you're going to get some NAPL into your sample, either by pumping or by sorption to a passive sampler. This photo at the bottom shows what happened to a droplet of weathered PAH-rich DNAPL placed on the surface of polyethylene. And basically it preferentially wets it. It just coats it. So The question is, how do we get reliable pore water concentrations, which again is the bioavailable phase, in direct contact with NAPL, which is in the sediment, without getting any NAPL in the aqueous sample? And the answer is to use porous ceramics. Porous ceramics are water wet, preferentially. They have pore sizes on the order of low single digits microns. So NAPL can't get through them. In NAPL mobility parlance, it cannot exceed the entry pressure and go through ceramics. So you can pump water through them, even in direct contact with NAPL, and pull only water through. You can put clean water in them and then deploy them and collect samples by diffusion. You can collect samples either in situ or ex situ if you have bulk sediment that you've taken to a laboratory. So this method allows us to get accurate pore water concentrations even in direct contact with NAPL, which is so common in sediments at MGP sites. Okay, what about NAPL? So the NAPL phase has three primary transport mechanisms that we need to quantify. The first is flow through the pore spaces, or advection. The second is ebullition, gas ebullition, facilitated transport. And the third is post-cap consolidation. So if we put a sediment cap on top of sediment, especially if the sediment is relatively soft, it will compress, it will squeeze. That could potentially displace NAPL out of the pore spaces of the sediment below the cap. So we have to look at all three modes of transport. And for NAPL advection, we have a similar equation, and the mass flux is basically the density of the NAPL times its flow rate. I mean, it's a pure chemical phase in essence. So we want to know what the mass of NAPL is over time. So the flow rate of the NAPL phase can be broken down to the hydraulic conductivity of the NAPL in the porous medium times the gradient that's driving it. I'd call that the net hydraulic gradient. And the gradient is actually reasonably straightforward to estimate based on an estimate of the NAPL density plus the hydraulic gradient. But what about the NAPL effective hydraulic conductivity? You have to be able to quantify that. So common methods to estimate the hydraulic conductivity of the NAPL phase itself are to look at rates of NAPL accumulation in wells and then calculate a NAPL transmissivity value. And based on the thickness of the zone that is yielding that, you can calculate the hydraulic conductivity of the NAPL phase itself. Or else you can estimate it based on this equation. You can estimate the relative permeability of the NAPL phase, and then you've got a hydraulic conductivity of the water phase that you measure. And then there's the ratio of the viscosities. So that's another way to try to get at it. But there are potential pitfalls in using these methods. For starters, in sediments, it's very rare for NAPL to come into a piezometer or a temporary well or whatever. Of a wide variety of sites that I've worked on over the last 30 years, I've only seen NAPL come into 2 piezometers in one small location at one site. And in those situations, we don't know how fast it accumulated. We just know we put in a piezometer, we go back and pull a transducer out a month later, and we know that there is some NAPL that has accumulated at some point. With respect to the calculation methods, that's fraught with a bunch of uncertainties. And so what we want is a much more direct way to measure the hydraulic conductivity of the NAPL phase itself. So it's very common when you're evaluating NAPL mobility at any sites, actually, to do laboratory NAPL mobility tests. And with these tests, you take a sediment sample that has some NAPL in it, you subject it to a hydraulic gradient typically that is much stronger than what exists in the field. You drive NAPL out of the sample, and the laboratory reports the volume of NAPL that came out, the initial and final NAPL saturations. And so you can calculate based on the volume of NAPL that came out over the duration of the test with a known hydraulic gradient and a known geometry of sample, what the hydraulic conductivity of the NAPL phase is in that sample. And that accounts for basically anything that influences the ability of NAPL to flow, like the viscosity, like the saturation, like the wettability, like the pore sizes of the material. So by using the test results more fully, you can get a direct measurement. And of course, you don't do this once, you do this with a bunch of samples so that you get a good sense of the range of NAPL hydraulic conductivity. And of course, you also test some samples that have the highest saturations. And what we found is that typically NAPL has little or no potential to migrate in sediments. And often when we calculate the NAPL effective hydraulic conductivities, we're getting values that are really low, that are typically 10 to the -7 would be on the high end. 10 to the -8, 9 centimeters per second is more typical. Okay, well, what about gas ebullition? So in subaqueous sediments, it's common to have a methanogenic zone that generates methane. The methane can nucleate into gas bubbles, and depending on the sediment conditions and the gas generation rate, those bubbles can fracture the sediment and move upward. And if they move upward and contact NAPL, you get a situation where the methane bubble is coated with NAPL. It's kind of like sheen formation. You've got a gas phase and a water phase, and it spontaneously spreads out and covers that interface. So you get a NAPL balloon with methane on the inside, and as it goes up through the surface of the water and breaks at the surface of the water, you can get sheens on the surface of the water. And that's another issue altogether, but that's something that typically needs to be mitigated. So there are multiple factors that influence how quickly this sheen blossom production occurs. And typically what we want to do is measure the fluxes at a time when the sheen blossoms are the most prevalent and the most abundant, the fastest. And that's when the water levels are relatively low and the sediment temperatures are relatively high. So there are a few different ways to get at this. There are visual methods. So sheens have different colors, and ASTM and NOAA have published estimated thicknesses of sheens based on their color. So you can go out and you can see where sheen blossoms are happening, how frequently they're happening, how big they are, what their color is, and you can estimate mass flux that way. A way to get a bit more quantitative is to actually sample the sheens themselves. So when a sheen comes up, you can get a sheen net, which is this hydrophobic material that you just contact to the surface of the water where the sheen is. The sheen wicks into the net and you send it to the laboratory, and then they can tell you in detail the mass of whatever parameters you're interested in that are in that sheen material. The third method is to use flux chambers, which are these sort of inverted domes. And when the bubbles come up out of the surface of the sediment with the NAPL coating them, they go up through this dome, and then they go up through a column above that through a NAPL trap, and you can put in glass wool there that strips the NAPL off of the gas as it goes up through it, and then you can analyze the glass wool. There are pitfalls to each of these methods. If you use a visual method, for starters, the sheen color is just a general indication of thickness. And it can vary from site to site, potentially based on the different properties of different NAPLs. And so using a visual method alone is imprecise. And then there are also different conditions like wind and waves and rain and weather that can influence collecting visual data. Sheen blossoms might be tough to sample with sheen nets if they're happening too quickly, and sometimes they're happening very quickly. Flux chambers are really quantitative, but they're expensive. And sometimes they're hard to position into place without disturbing the soft sediment and without creating additional ebullition pathways. They can be hard to install on surfaces that are hard also. And in very shallow water, it's difficult to use them. So one way that we can collect continuous detailed visual data is to use a reference frame of known size. And then we can just collect video. So we can watch the sheens developing and accumulating in a specific spot, and then use that information combined with sheen nets to get quantitative estimates of the mass flux due to sheen blossom formation, due to ebullition. So we look for the areas that have the most abundant, fastest sheens during a time with low water, with warm sediment temperatures, and then we collect the visual data, and then with separate sheens, discrete sheens of known visual characteristics and size, we can scoop them up with sheen nets and get a number of measurements of sheen thicknesses for specific sheen colors and sizes. So if we take a video image, and we've got a starting point right here, and then several minutes later, there is more sheen on the water surface, we can take those images and digitally rotate them so we're looking straight down on them. And then we've got these sheen areas of different colors, and we can just map them out and get an accurate representation of those areas. And by combining this with sheen net samples, we can calibrate the thicknesses of the different colors and then get what we think is a quite accurate representation of the mass flux due to ebullition. All right, what about consolidation? So if you place a sediment cap on top of soft sediment containing NAPL, the pore spaces will squeeze, the water will come out, the NAPL will come out to some extent. So the question is, to what extent? How much NAPL may move upward? And there aren't any standard methods for estimating this. But the potential pitfall is it could happen, and we need to be aware of that potentiality, and we need to account for it. So the way that we can get at this is to measure the geotechnical characteristics of the sediment. And then based on the cap that we're thinking about installing, we can use modeling to estimate the long-term consolidation of the underlying sediment. And based on the anticipated compression of the sediment plus its initial porosity, initial NAPL saturation, estimates of NAPL viscosity, we can estimate how much NAPL could be squoze out of the underlying sediment. And in almost all cases, we conclude that that mass flux is negligible. It's very minor in comparison, typically, to ebullition. Ebullition is actually typically the main driver. But this is a way to use existing information to develop an estimate that you can account for in the design. So wrapping it up, we know chemical mass flux is crucial for successful sediment remedies, and we have to look at the dissolve phase plus the NAPL phase, and we have to look at multiple mechanisms for potential NAPL movement. And there are a lot of different measurement methods for these parameters that we need to combine to develop a successful design, but there are pitfalls with each one. Fortunately, there are economical ways to get around some of the complexities to collect good, reliable data and quantify mass flux effectively and get good remedial outcomes in the end. So that's it.
Okay. Sorry. Oh, certainly. Okay. And I just use this controller here to advance. Thank you very much for that. Appreciate it. Okay. Give me a second. I like to have a timer to keep me on time here, right? Okay, good. First off, thank everybody for taking time today to not only be at the event, but in our session. Started a little early, some great talks and some interesting stuff to hear about. So today I'm going to be giving a presentation called Innovative LNAPL and Mass Recovery. What's a little different about me compared to most people in our industry, I'm a synthetic organic chemist. What's that mean? That means I can go into a lab and make a heart drug for you, an alkaloid, a lot of really complex things. I have a really innate understanding of these contaminants, which are quite frustrating for a lot of us. And I see it very much from a chemist's perspective. And then I did something very bizarre in the late 1980s. I walked across the campus and did geotechnical engineering, other than getting myself extremely in debt and questioning the move that I made. Looking ahead 33 years later, it was a good move because I learned a lot from it. Later got a master's in project management. So I'm going to give you a bit of a different view on a lot of things from a chemist perspective. Although I appreciate our engineering way of looking at things, it's quite different when you look at it from a chemist perspective. So I'll be actually talking a lot about that today. And just, okay, here we go. So these are some images of the typical stuff that we deal with at contaminated sites. So I'll speak about who my company is briefly, because that's less of what I want to talk about today and more get into the meat and potatoes of what we're doing. We've been around for going on 30 years and a few years. We've won a lot of international awards. I've been in over 50 countries in the world doing stuff. The key thing that I developed was I looked at the behavior of contaminants and said, hey, if they're behaving this way, is there any ways we can modify that or change that to make contaminants more available? Why they're not available is new for you guys. We've been dealing with this for hundreds of years as chemists because we've always been trying to improve reaction kinetics. And we're as frustrated as you'll get out, but we figured out ways of doing that. And I'll be presenting some of that today in a short sense. Something else is you'll find out about chemists. We like purity. It's beat into us like with a 2x4 as we're going through our undergrads. They don't like seeing impurities and stuff. So one thing about the products I develop, there are no impurities in them. And some of the stuff to parts per quadrillion can't help it. It's just the way things are. So just want to let you know, you don't have, so due diligence has been undone on that front. And it's really important. We're working globally. I've done since June over 75,000 miles globally, just trying to reconnect with our friends and people. I've done more hugging of people that I haven't seen in a long time than you want to know. So it's been nice to get back out there and do that. We created some relationships with people here in the United States to make our stuff available to a number of hubs throughout the country. So everything's basically a couple of days out. You guys are great because you plan well for your sites. You don't need something tomorrow. You might need a water level meter or something like that tomorrow, but as far as products, you're pretty much well organized in making that happen. So again, because of my background from organic chemistry, I tend to take more of a, should we say, a medical perspective on looking at patients. I've actually done sites where they refer about healing the site when I'm at places. It's just different language used by different people in different countries. So you may hear me doing a little bit about that. Now, when we're dealing with contaminants, of course, we're talking manufactured gas plants here, but the sources from our anthropogenic activities include above ground spills from above ground storage tanks, below ground storage tanks, pipelines. We transport fuels by rail and by air. Spills happen. It's going to continue to happen, right? So as a consequence of those, they land onto the surface. If they tend to be very small molecules, you might notice you'll get that smell in the air because they're VOCs. Now, when they enter the geology, what's going to affect their movement? It's simple. It's physical. If you're running through a bunch of alder trees, you're not going to get through very quickly. If I run through the redwoods, I can run a mile a minute. It's really, really easy because there's lots of space. So that's obviously the texture of that's going to affect it. Sure, gravity is in play. If we typically think about things as being L-NAPLs and D-NAPLs, that's okay, but you guys are missing that whole crowd in the middle. But we'll get into that in a moment. So we tend to see things like they're light, they hit the groundwater table, they move along its contour, again, following gravity. If they're heavy, they sink along that surface and they work their way down, okay? And obviously confining layers will affect that. The movement is obviously affected by a bit of gravity and again, texture and groundwater flow. This is an interesting baler because at the top of that baler, there's LNAPL. This is from a manufactured gas plant. There's DNAPL. What's going on in the middle? Heaps of compounds in there. So to me, they're obvious what's in there and what we had to do to get them out. So yeah. And the other thing too is when you're dealing with things like VOCs or semi-VOCs, don't forget them. They're part of the package as well. They don't care if it's an LNAPL or DNAPL, they go along with it. As far as the ability for that bulk liquid to hang on to, it's like a mother holding onto a baby's child. There's not much contact. It will slide off. It will go out. So we have a different way of looking at things, and the behavior of those and predicting those behaviors compared to something else has the ability of those should we say contaminants or bulk liquids to hold on to things. And you got to look at it from a different way as a chemist, but you can still use other measurements that we like as engineers to interpret that. But we'll get into some of that today. So when you're dealing with elm apples, we know that they don't easily dissolve or mix with water. They tend to want to phase partition, and we tend to talk about them in terms of being light, non-aqueous phase liquids that want to float like this image, or they're dense and they want to sink like you'll see in this next image. That's only part of the answer to what's really going on. And when these things get into grains, like you've heard about sediments or fine grain materials where there's a lot more surface area, like, by the way, if you took 1 quart of clay and 1 quart of sand, 1 quart of sand has the surface area of the size of, let's say, a good sized boardroom. If you want to go watch an NFL football field, that surface area they're playing on is the amount of surface areas in that 1 quart of clay. So just to let you know, there's a lot of surface area for things to grab onto, right? Well, when they get trapped in, they cause pathway interference, and groundwater can't move through them, it moves around it. It has no choice, just the way things are. So what I'm going to talk to you today is a little bit about some other factors that, from a chemist perspective, interfacial tension. What's that? Aggregation, not agglomeration. What's that? Sorption. We've heard that term brought up. I used to bring it up 20 years ago, and I had people look at me like I had a horn on my head. There was something weird with me. So here's an interesting drawing to show you how liquids behave. There's lamp oil floating on rubbing alcohol. There's a soda cap in there, by the way. There's some vegetable oil. There's a bead, water. There's a cherry tomato, which we know has some water in it, so it's intermediate density. Soap, a layer of dye, milk. Drank some of that today. Some maple syrup. There's a popcorn kernel, which is pretty dense, but it actually can float depending upon the liquid you're dealing with. Corn syrup, honey, and there's a brass bolt in the bottom. Why is there so many liquids layers? It's because things have different densities, so it will dictate their behavior. So it's not an absolute floater or sinker. There's a bunch of things going on which will dictate how it's going to behave. And if you're a good detective, it's the better you understand the criminals, the better you can figure out how to catch them, right? So kind of like that, a little bit of forensics going on to it. The other thing that comes in place is when we're dealing with things moving through things, we tend to forget something called steric hindrance. Little things move easier through fine grain geology than bulky elephants. So a chihuahua is going to get through an alder forest much easier than an elephant. So there's factors like that that come into play. Anyways, moving along, and then there's VOCs. Yeah, you can't ignore them. They're there. So the show right here is just talking about the brown being obviously the geology, blue being the water, green being most of those hydrocarbon or chlorinated solvents you're dealing with, and the white is gas. Gas bubbles form. And since they don't dissolve in water, unless they can do hydrogen bonding with water, they're going to phase partition and sorb. And then if you have enough of that concentration, they're flowing globules or ganglia. At a higher concentration, you're going to see measurable L-NAPL or D-NAPL or sheen, as you've heard previous speakers talk about. So there's interfacial tension going on between those phases of contact. There's aggregation going on within that bulk chemistry of water, as well as the contaminants. And then when they don't dissolve, they sorb. So just bringing some other ways of looking at what's really taking place here. And when you look at it from a different perspective, you all of a sudden gain increased insight. And that's where I come at things. Now, to give you some simple principles that you can relate to, water has a surface tension of 73 nines. Ever done a belly flop in a swimming pool? I remember the first time I did as a child, I cried my face off in my mother's arms as I realized, don't do that again, it hurts. I jumped off a diving board, I think it was a 4 or 5, it hurt. Now you take most of the contaminants you guys are dealing with, petroleum hydrocarbons, chlorinated solvents, look it up at CRC Handbook of Chemistry. Surface tensions about 21, 22, 23, don't really care about it, doesn't matter to me. But you all of a sudden see that plane of contact between them is rather interesting. Solubility is at play, for sure. But what's going on with those bulk liquids? And by the way, there's a big difference if it's fresh water versus salt water. If you got gases emanating into fresh water, I tell you right now, they will emanate much slowly into salt water. If someone wants to explain as to why, the chemistry isn't well established for hundreds of years. But what they don't really talk about very much is what happens at that contact plane. Let's pretend for a moment I have pure benzene coming in contact with water. Let's call it pure water for the sake of argument. Benzene has a surface tension in the low 20s. But you know what happens is at the contact plane with the water, given enough time, the benzene molecules will reorganize themselves significantly. This happens with all contaminants. You guys don't want to talk about this. And what happens is the surface tension, if you go into the efforts of measuring, this has already been done, will actually increase to about 35 to 40. What's going on here? Whoa, what do you mean it's increasing? I thought it was just, it is what it is. No, there's a little more going on here. So that means that imagine that water comes into contact with that trapped globule or sorb phase, it's going to move around it or over it. Sure, a certain amount can get in, but it's going to be limited by a function of solubility, if you want to look at it that way. And if you do get something that does dissolve in water, such as MTBE, what happens to that bulk back end of it? it grabs onto other contaminants. That's what when he saw that vapor coming up, it's grabbing other contaminants that will grab onto those VOCs, because like dissolves like and like attracts like. That's why MTB plumes move much more quickly than ones that are completely neutral. So aggregation is something that you need to really think about, that bulk behavior of how these want to behave, and given enough concentration, you shall get it. It's just a function of chemistry. We can't get rid of that. So it also affects why you're seeing L NAPLs and D NAPLs. And I like to use this expression, like dissolves like, or like attracts like, or the medical analogy of clogging up arteries when we're looking at what we're dealing with. And by the way, all the fine arteries and veins and whatnot through my body are much bigger and much grander pathways than what you have in most of the geology that you guys are dealing with. So transmissivity has a lot of challenges, even moving water. And we know as a fine grained geologist there, K goes down, right? So that causes issues for you guys on delivery as well as extraction. As a chemist, I like all the techniques that are through the chemically behavior. Did you know that when you're injecting an ISCO product, I don't care which one it is or the vendors, I've got no preference. The surface tension of those products are sitting up in the 70s. Try injecting those into finer grain geology, you can have some issues. So just saying that those are factors you'll have to overcome, and of course, techniques are developed. But here's just showing some veins, and imagine that stuff builds up. And for myself at my age, I got to think about stuff like this. I watch my diet, but as things start to clog up, it causes issues. That's why some people get stents around their heart to open up some of these pathways. Well, you can reverse some of this way chemically, by the way, your doctor can. If you guys don't know how to do it, talk to me and I'll tell you there's ways to actually reverse some of this buildup in your body. Yeah. So we talk about agglomeration, where these particles come together, which is quite a nice physical process, but it's completely different with chemistry. It's aggregation. And again, like dissolves like, and it comes together in a very orderly manner. It's not haphazard by any means. It's very orderly, very predictable, much more than you'd think. So we get this phase partitioning occurring, floating, sinking. That's actually frac sand for upstream oil and gas. That's actually drilling cuttings from people, let's say in Texas. And there's this highly contaminated soil where you got all those factors coming into play. So we talk about absorption and we talk about contamination, whether we're using physical, chemical, or biological methods. Only things you have are those three or combinations thereof. They all fall in those categories. And you're dealing with, say, contamination, NAPLs, zorb phase, or globules. They will tend to phase partition and zorb onto that surface. Okay, and they're less available to you for all those methods, whether it's biological or whatnot. And I'll actually give it a reference about biological here, because we've been dealing with that for a very long time, as in centuries and thousands of years, biological degradation of a lot of things. So if you can phase partition that and get that back into solution and still maintain its availability, you've really broken the rules of chemistry or hydrogeochemistry to improve your ability to contaminate, to remediate those contaminated sites. Okay, this is just fundamental chemistry I'm looking at. And I don't care if it's VOCs as well. And by the way, I look at VOCs and we go non-aqueous phase liquids, non-aqueous phase gases. We don't use that term, but they are. As chemists, we tend to think of that way because there can be a pain in the backside when we're doing certain reactions. I like this quote that's coming up right now. It says, during the past decade, this is from 2005, during the past decade, much discussion has centered on the unavailability of zorb compounds to soil microorganisms. It is now generally assumed that the absorption diffusion of bound contaminants to the aqueous phase is required for microbial degradation. So I often do a lot of stuff where I'm helping people do something called surfactant enhanced bioremediation. Just came from a large project in Africa doing that. So it's really important to even look at things like absorption. I spend a lot of time on that because that's one that you guys can gravitate to, but it's not the only factor. There's about 8 I like to look at. There's 3 I spend a lot of time on. If you guys got the appetite, I'll bring up the other ones, but I'd have to be careful. So when we're looking at absorption and its shear effects, because we all know what's happening, it limits the physical availability, whether you're doing multi-phase extraction, thermal, soil washing, the list goes on. If you're doing biological, aerobic, anaerobic, or facultative, it causes issues for those. And then chemical processes. Since I got a bunch of people in the room, you guys spend a lot of time on ISCO and ISCAR, and I know there's another chemist in the room. There's 4 other class of reactions you guys aren't doing. Still don't know why. I still don't know why, but you're missing them completely. So do a Google search. You might catch on to it. Come talk to me. And I'll probably have to do some work on those to show you guys them. So when you're dealing with contaminants and you want to have a better predictability on treating them, contaminants absorb to surfaces. But for me as an organic chemist, I didn't like using bulk surfactants because they don't have any preferentialness. You have to use them in high concentrations. They have to form micelles or emulsification. And as an organic chemist, when I'm doing a reaction, I know that I bring this together, it's going to cause a nucleophilic attack at this location and result in some novel compound or an intermediate towards something that I'm building. It could be a hard drug. So I like predictability. Lack of predictability makes things really horrible for me because I'm very OCD. So in the case of what my surfactants has been 4.5 years dividing ones that could differentiate between the ear, the nose, the arm, the hand, the foot. So what I like to do is having that affinity, I can be applied at very low concentrations, and I can have an interaction with that without causing a emulsification. And up in the upper right-hand corner is showing you how typically over 95% of surfactants work. And many vendors rely on this. I don't believe in this. And by the way, your body uses more along the lines of what I do. When you start looking at when you're eating oils and things like this, you have glands that leaving your stomach, getting it around the complication of your pancreas and whatnot to help basically get those into solutions. You can use them as foods. So it's not entirely true. And by the way, bacteria do what I talk about. So we developed a number of different products to deal with the selective nature of what you're dealing with. Not just one bullet kills everything. I don't believe that. You need a mixture of things. And because that, you please dilute my stuff in low concentrations. I'm a guy, more is always better, right? Well, in chemistry, sometimes less is more. We actually use that expression a lot. We've even developed some stuff more recently for dealing with PFO and PFOS. If you got sites and you got a lot of organic content, I heard some reference to peat. Watch out what'll happen when you have that stuff present when there's natural occurring organic matter. And as we know, a lot of our world has been forested. Well, those trees break down. There's a lot of organic matter left by their roots in the systems, right? So think about that. So another thing I'm gonna do right now, because I'm a weird guy, did anyone ever tell you that what's water? Water is H2O. No, it's not. Did you know NaCl doesn't exist? What? A plus D does not produce 100% of C in reactions. I won't spend too much time on that, but just showing as a chemist, there's a little more truth to that than what you're being told. Actually, NaCl from a crystal perspective, you guys remember your crystallography courses from geology? Yeah, I remember I walked across the campus. It's one Na at the center communicating with 1/6 of the surface area of 6 Cls. 1 times 6 times 1/6. Oh, 1-to-1 ratio. That's what it is. So it's not really telling you exactly what it is. So is water really H2O? Well, not exactly. Therein lies some of the things that we have to understand. We do know that water is polar, that the oxygen is more electronegative than the hydrogen. So they act like magnets. We all have heard about hydrogen bonding. They hear about it in junior high school. But unless you really get into a lot of in-depth chemistry, you don't really spend much time here. They actually communicate with other water molecules three-dimensionally and reaching out, and they keep reaching out. This is what you're pushing and pulling through geology. There's people who've been doing research on this stuff for over 100 years. Water clusters are not new. You tend to think of things in that very simple generality of water's H2O. If it was, I tell you right now, like a Formula One race car, it should race right through silt and clay. If it's really H2O, it's not. This is what you're dealing with. Now, I'd like to tell you there are ways of actually making those clusters smaller. And I'd like to tell you, I thought of the idea, actually read it in biochemistry where bacteria were doing it. And using biosurfactants. So that also prompted part of my research to try to find ways, not only making things miscible and more available, but manipulating water, because you guys have to deal with geology, you have to deal with contaminants, you have to deal with water. There's a little more going on than that, but those are the three principal benchmarks you have to be able to manipulate. And I knew I had to work within that. By example, if you have these large clusters, you're trying to deliver something and you got the Zord phase or blocked off areas, you really can't get in there. But if you can make them smaller and smaller, you get access. Imagine a fireman or woman going in, they want to put out the fire. Well, if they can't get into the building, they're going to really be challenged. You have to get in there, be able to work on that and be able to make that stuff more available if you do something physically, chemically, and biologically. And for the record, I'm none of those three things. I'm not a physical, chemical, or biological treatment system. I'm not. Sorry, I'm not. But I can make something more available if you need to. If what you're doing is working, stick with it. If you need help, give me a call. I just found a way to break the rules of chemistry, just showing some of the stuff that we've done. So there we go. We start dealing with that whole idea of that contact plane. So if you start changing the surface tension of water down to 30 or 40, and I just told you that those contaminants tend to be down there. And even if they reorganize, wow, they're about the same. Oh, interfacial tension becomes less of an issue. The other thing I do is with surfactants, we're always talking about bringing oil into water. Okay. But you know, as chemists, we don't just rely on oil and water. You can bring water into oil. You can go both ways. You guys have been on a one-way street, you can. So I actually found a way of doing both. Why rely on one system? We can use both. Your body does it too, by the way. So it's not completely novel. Just showing they're just doing some phase transitioning to try to increase the availability of some of this stuff for sites. Okay, we typically do things where we have people injection wells, or they're vertical, angled, horizontal. We also have some cases where we have a pipeline, a roadway, a building in the middle. You have to inject on one side and pull at the other. I'm going to try to show an animation. I don't know if the gentleman in the back can actually tap on the bottom left-hand corner of an animation if it comes up. Oh, I don't have it yet, so it'll be a little while. But there's just a link if anyone wants to see that stuff. So what I'm gonna do right now is I've got about 7 more minutes. I'm gonna spend some time talking about a manufactured gas plant that was quite a complex property. It's about 100 years old. This is down near Melbourne, Australia. I was able to collaborate with a company called Blue Sphere and their contractor Enviro Specific to bring forward a solution to a very complex problem. a lot of coal tar type stuff that you see in a lot of these manufactured gas plants. Again, being an organic chemist, I had to work on coming up with a formulation that would work on this, gave me samples, had to go in the lab. Was it frustrating at first? Yeah, it was. I've been given bitumen samples of people. Is it frustrating working? Yes, they are. They're completely different beasts. Had to work on formulations that would work on them. Sometimes my work is a bit frustrating, but all I'm trying to do is increase availability for methods that you're conventionally using right now. Those methods will mature and grow. And by the way, in December of this year, our industry will become a yet 51-year-old industry. Remember that the US EPA was only formed in December 1970, and the first Earth Day was in April. We're a young industry. We're still growing, and I'm blown away by how much we've done in the last 50 years. So we look at these sites, very similar photographs that you see from a lot of people. It was a rural gas works, as a lot of them were rural, and now they've been overrun by agriculture and domestic developments. This is just showing you some of the old structures that were there. Let me go back for a second. There we go. Some of the structures that are there, typical of what you see in the manufactured gas plants. Again, this was in operation for 100 years. And what they tend to do in a lot of industry, and not just limited to these guys, when they had waste to get rid of, they basically would put them in wells nearby or surface dump them or dig a hole and put them in there. Not uncommon. I see that around the world. So it's not just what we're seeing here. It's a practice everywhere. And these guys even have not only residential, but agricultural activities nearby. What's interesting in this is you can see that the two main plumes that are there, and they kind of brought out in the upper right-hand corner and bottom left. What's interesting is you can look at certain indicator chemistry. In this case, where they had naphthalene was quite indicative, where they would have these L-naphthalene and D-naphthalene in between compounds. So it was an interesting correlation they made. I could explain why to some if they're interested, but that's kind of cool. And the challenge there was they wanted to obviously clean this area up for redevelopment and look at the encroachment they were realizing from residential and agricultural activity in this area. So it's a real big push to do so. What's interesting in Australia compared to here is they actually have assign an auditor. So not only are you working with the regulator, your client, and you're the consultant doing it, there's a separate consultant who has special skills or qualifications that actually sits and observes every single thing you do and is involved in every decision. So it's kind of funny to have a peer sitting there. Interesting process. Yeah. So what's nice about this site is when you have a patient come into your office and they're not feeling really well, oh, here, take this pill. No, there's a little more involved. As we all know, you take some time with that patient, find out their history. What brought them into your office? Why are they not feeling well? In this case, they did a great job of evaluating this site. They had over 100 wells installed in this site. So they had a really good understanding of the hydrogeological setting, the contaminants, where they were. And it also made my job a lot easier in understanding these non-aqueous phase liquids and how we might look at ways of attenuating this. And essentially, for all intents and purposes, they were used like a multi-phase extraction type system. Of course, when they first operated that, they got some mass out, looked pretty good. And you'll see this at a lot of sites. It works great. What happens? It gets all the readily available stuff. The stuff that's less available doesn't come out very well. Don't throw the baby out with the bathwater. Multi-phase is wonderful. Even work at liters per minute. Forget gallons per minute. Establishing hydraulic control. If you can find something that can then release that, those systems are really good at capturing it. So just want to know that sometimes you can look at pairing technology. I even saw some talks over the last couple of days where somebody's using one technology paired with another, 1 + 2 = 3, or 3 or 4, and the result was just magic. Just really impressed with seeing that happen. And by the way, it's not just limited to our fields. It's happening in IT where they're merging things together. It's happening in medical fields. So I'm glad to see we're taking that on. I explained to you how the IV sol works, how we're making stuff miscible in a selective manner without causing emulsification, which is important because if you cause emulsification, try managing that wastewater. Run it through an oil water separator, it'll happen. It won't phase separate. And then it's going to create a lot more challenges to your activated carbon, your MySlicks, your membrane separation, your bioreactors, the list goes on. I have no preference over any of them. You obviously will be designing them towards what you need. This shows them getting set up on the site. Where again they were looking at surfactant enhanced aquifer remediation. We went from bench scale to pilot to full scale. So sharing some of that with you. What's really nice about this, they got a real kick of the fact that they were thinking that we should be going at concentrations much more than 1 to 25 or 1 to 50 dilutions. And they had to get on the phone and say, trust me, just trust me. They really didn't think that would work. And they were quite surprised by the results we got during pilot scale that it was effective. And they agreed to stay at those lower concentrations. Otherwise, they're going to be wasting products. I'd have made some more money, but that would be inappropriate application of science. So can you click on the bottom left-hand corner of this to see if you can get that animation to run? Let's see if we can do it. Got a couple minutes left and I'll be able to finish this one. Can you see it? Ah, there we go. As all of you do your investigation, your site to see where the soil, the groundwater, the vapor contamination is, where the LNAPL is, where all that kind of challenging things are, right? And when you do that, we can actually model around this case. This can be a push-pull. We can put some 4-inch wells, core screened across that smear zone of contamination. And what we can do there is gravity or very low pressure injection into that. You can use packers to help direct it if there's a certain depth interval you want. And then inject that in, and what's happening right on contact. Right on contact, it starts working to make this stuff miscible. So it's going to make a certain amount of that stuff phase partition into the aqueous phase, after which you're going to extract it. I would say 90% of our processes are you inject today, you extract tomorrow. So you can actually do 3 of these in a week during a pilot if you want to, and that's pretty common. And what happens is each time you inject and you pull stuff out, you're doing something that's been going on for about 400 to 500 years, maybe longer, that I'm paying attention to, called a sequential extraction. We've been doing it in chemistry all the time. Every sample you send to the lab does something like this. I just took the idea of taking surfactants and attenuating that and getting some of that out. And if you're ever looking at a site where you have a lot of free phase, you're trying to do certain physical, chemical, or biological processes that are challenged, if you get rid of that free phase or get it down to a bit, all of them will work much better. If you have 3 or 4 feet of product on there and somebody's telling you you should be using an ISCO product, I'm going to tell you 2 things are going to happen. One is you're going to be doing multiple applications. It's going to be very expensive, and it shall fail. If it doesn't fail, I'll just tell me how much money you spent to overcome that. You should get rid of that free phase first, in my opinion. So here's just showing some of the results that we had at that site. Again, there's that LNAPL, DNAPL in between. And because we were aware of the chemistry and we looked at those details and we spoke every single week while they were doing this work, you can see how in the balers it got less and less, to the point where there's different locations on the site. To they were getting a sample, you just see this little globule showing up in the bottom. So not only are we physically seeing this, we were also taking samples to verify this, and so on and so forth. There was multiple lines of evidence to observe what we were doing. And remember, there was an auditor on here, not an easily convinced auditor, by the way. So they really had to do their work properly. So again, both visual and quantitative data. And I'm again, coming from my background as a chemist, I like multiple lines of evidence for everything. And you're seeing that crouching into a lot of areas of even medical processes and things like that. This actually shows you a graph of the daily NAPL recovery. It's almost weekly, and some of the stuff they're doing, total mass recovery. And what you'll notice, some of those times there's big amounts coming out. Early on, we were treating certain areas generally on the site. And then what we did is when we started to clean up certain wells, then we started to double down our efforts in the remaining wells to get that stuff out. And then it got down to less and less and less until we completely resolved it. So it was a really nice application. So the conclusions for this are really quick. They found the SEER application to be quite effective for the soil and groundwater impacts with these NAPL compounds. They also found it was really good because we had limited human environmental receptors, because this stuff wasn't emanating into the homes or whatnot, a lot of unconsolidated soils. From the permeability perspective, obviously there was some issues there, but we obviously helped overcome some of that by changing the water clusters and making things miscible. It was very sustainable, economical. They found it to be much more effective from a cost perspective and whatnot than some of the alternatives that they looked at. And they obviously had an auditor involved in this thing. The nice thing about this, the system was closed off in early 2021, and I believe the site's been since closed. So I'll stop with that one. And I'm just going to go to real quick to put up my contact information. Sorry, only have so much time today. There. Oh, sorry. Happy Thanksgiving. There you go. I never made it to it. Here you are.
We'd like to thank the panel for their presentations this morning. And I would like to make a couple of announcements. If you want to have copies of these papers and go through them in more detail, they are available online, as is the entire conference. If you need continuing education credits, those forms are available at the registration desk. And if you have questions, we'd be happy to entertain them. Yes. Speak up, please.
Thank you. Yeah, so my question's for Bud. I'm with Provectus. We do a lot of ISCO work. And I'm just wondering, if I have a site that comes to me with a lot of LNAPL or DNAPL beforehand, before I'd want to go out and do any injections, how does the removal of that NAPL, impact the stoichiometric demand for future ISCO or ISCO applications afterwards?
First, I'd like thanks for using that word stoichiometric. It's really important. I don't hear it enough. If you sit down and do the math on floating product, and I'm not talking a sheen, I don't get too excited with sheens, but if you've actually got measurable product inches to feet, and a lot of it have to get this 0.01 feet of thickness as an objective at a lot of sites. If you do the stoichiometric calculation, you then realize what the cost of treating that LNAPL or DNAPL is going to be, both ISCO or ISCAR, not just ISCO. It's going to be very tremendous. As a chemist, I have to like ISCO and ISCAR. I have no choice because I'm a chemist. I think they're great technology when applied properly. So in the case of what you're saying, if you're living with products that deal with ISCO or even biological packages, by removing that, and we know high concentrations of contaminants actually will inhibit bacterial growth, lots of papers on that. But if you have LNAPL or DNAPL, by removing that, then following up your package, I suggest you'll have greater success at those projects.
Great. Thank you very much.
Any other questions? Yes, down front.
This question is for Rachel.
Yes, Rachel.
Regarding the samplers you had in well, what kind of duration do you need to have for those before you go back and collect them and have, measurable data? And then just curious about the kind of total duration of your the study period for all that field work, just how long that took.
So the samplers are sized and deployed for a period of time based on expected concentrations in the ground, but also the expected groundwater velocity. So you have to couple those two things together and make sure you're selecting a meter that's appropriate for that. We deployed those SP3 meters in our wells, and we didn't end up using that data because we didn't get enough groundwater movement across that meter. So we ended up using just traditional concentrations to support our study in the end at depth. And then the deployment time, ours were deployed for about 6 weeks through the study. But again, it varies a lot based on the type of meter, your velocity of the groundwater, and the concentrations that you have.
Any other questions? All right, we're supposed to go to 10 o'clock, so I'm assuming that you have earned a little bit of extra time. Thank you very much for your participation.